So some one-dimensional force problems. Important questions include the elevator or apparent weight problem, the air resistance problem, friction, and the many-body problem when there's more than one mass. We need to talk about this thing called the normal force. The normal force is the contact force between the floor and the object. Let me pause for a second. Okay. So the normal force is the contact force between the floor and the object. It's a Newton's third law force. The normal force is as big as it needs to be. You or the object push down on the floor pushes back with the same force. You want to increase the normal force? Push down harder. You want to decrease the normal force? Don't push down so hard. Give me 1 second here. I just need to pause the recording. So, interestingly enough, I wrote, the normal force is also the value that a scale would read if they were standing on it. Kiowa, my friend, scales don't read weight. Have I convinced you with my little experiment here? I hope. They read, and my abbreviation for normal force is F with a subscripted M. What you all think of as your weight is actually the normal force. What you think of as your weight is not gravity. It's the normal force. In fact, we call it the apparent weight, the weight that you feel you are. That's why on an amusement park ride, when you feel heavier, say if the roller coaster is at the bottom of the hill and pulling up or going through the loop, has gravity changed? No. What's changed? The normal force. In fact, any good amusement park ride just mucks around with gravity. Put your pencils down, look up. So what I wrote here is all of you right now feel your normal force equaling gravity. It's the apparent weight you feel. All an amusement park ride does is muck around with that. And we pay money for that. We like it. At least most of us do. I'm nuts about amusement park rides. Video, I just showed it to you. So here's our thought experiment. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. If a person with a mass M and a weight W is in an elevator standing on a bathroom scale, but you know what? First of all, what does a scale measure? And we're going to make this scale, instead of having it read in kilograms, let's just have it read in newtons so we can go straight to force. If the elevator starts at rest and accelerates up, what will the scale read? Their weight, W, more than W, or less than W? And convince me. Who says A, the scale is going to read W, their weight? Who says B, more than W? 8, 9, 10, 11, 12, 13, 14. Who says less than W? 1, 2, 3, 4, 5. Convince me. I can convince myself with no English, with a picture and an equation. What's my picture going to be? You know what? This is a job for a free body diagram. Okay? Here's the person. What are the forces acting on him? Get the obvious one. What else? Are they in free fall? So there has to be a force upwards. Is the force upwards going to be bigger or smaller or the same size as gravity? Hey, which way are they accelerating? I'll really exaggerate it. What force is that? Well, it's the floor. Oh, what's the name that we gave to the floor force? Manny. There's my free body diagram. If you're in an elevator that's accelerating up, that's what you look like. Who's winning? Minus. Who's losing? And winner minus loser always equals MA, my net force. This question asked about the scale. What does a scale read? Normal force. Let's get the normal force by itself. How would I do that? Add it to the other side. So you get this. The normal force equals mg plus ma. You could write ma plus mg, but I wrote it this way for a reason. Right now, all of you, right now, what's your acceleration right now? 0, which means right now, that's what all of you are feeling. If you're accelerating up, what that must mean is you're adding something to mg. If you're adding something to mg, is the answer going to be bigger or smaller than mg? Right? There's a proof, no English, a good free body diagram, no words, and an equation. It must be, if normally, no pun intended, the normal force is mg, I just did the physics, and it turns out that if I'm accelerating up, I end up plussing to it. Must be bigger. Example 2 says write a net force equation. I just did. I like example 3. I like example 3. I like example 3. 3 is a nice question. A student stands on a bathroom scale. Now, if you actually are standing on a scale reading in kilograms, what it does is it takes the normal force and it just divides it by 9.8. That's the scale that they put on there. If the elevator accelerates down, you know what? I would underline the word down. That's going to be important. Find the normal force, find the scale reading. Hey, this is a job for a good free body diagram. Right there. What are the forces acting on the student? Get the obvious one. Are they in free fall? By the way, how do I know they're not in free fall? If they were in free fall, what would the acceleration be? 9.8, not 2.25. So are they in free fall? Say no. So there must be a force pointing upwards. Bigger, smaller, or the same size? What direction are they accelerating? What word did I underline? Oh, so the force must be smaller. What force is that? It's the floor. What do we call the floor? And conveniently, if you happen to be standing on a scale that's on the floor, that's also going to be the scale reading. Well, that's handy. Who's winning? So my equation for part A is going to be gravity minus normal force equals ma. Winner minus loser equals F net, where F net is always just ma. You okay with that? What are we wanting to find? The normal force. Let's get it by itself. I'm going to do 2 steps at once if you want to look up, because what's in front of the normal force right now? A little what? I want to plus that to that side, and I'm going to, what's in front of the ma? A positive. I'm going to minus it to that side. Are you okay? I'm going to say it's going to be mg minus ma equals Fn. By the way, Alex, this explains why on the elevator, when it's accelerating downwards, you feel lighter. Are you lighter? No, gravity hasn't changed. But what do you think your weight is? The normal force. And look, normally the normal force is just mg. That's what all of you are feeling right now. If you're accelerating downwards, this would be your equation, and you'll notice then the normal force is your normal mass times gravity minus something. You're going to feel lighter. That's the feeling that you feel like you're going to fly out of the chair. You're not. But that's what we deal with the worst. All of us are used to an increased normal force. We're not used to a decreased normal force. And I think that's part of our evolutionary heritage. I think a decreased normal force meant that once when we lived in trees, we were going to fall. And we grab stuff. An increased normal force, like when someone dog piles on you when you're at the bottom of a swing, that doesn't bug us anywhere near as much. But a decreased one, like if you've been on the elevator, going up doesn't bug me at all. Going down freaks the snot out of me. I don't know if you're the same way, but that's kind of where I'm at. Oh, let's plug and chug. Did they give me the mass? Yeah. I have an answer. Nope. We decided to let down be positive. We're not going to put a negative in for the g. We took care of it right there. Yep. So it's going to be 35 times 9.8 minus 35 times 2.25. That's going to be the normal force. Which is what? Which is what? I didn't leave enough room here, sorry. I retyped this last weekend and I was lousy with spacing. 35 times 9.8 minus 35 times 2. Can I do this in my head? It's going to be the same as 35 times 7.8. It's going to be the same as 35 times 7.6. It's going to be the same as 35 times 7.55. 35 times 7 is going to be 210. No. Too many decimals. You get 264 if I go to 3 sig figs. Now that's in newtons. Is it? Am I right? Yeah. You're all participating now, I hope? Yes? Oh, that's in newtons. How do I change that to kilograms? I heard it, but I didn't hear it. Say it louder. Just divide newtons by 9.8. So if I go that divided by 9.8, the scale would read 27 kilograms. Instead of feeling 35 kilograms of mass, he would feel like he had a mass of 27 kilograms. Has his mass changed? No! What has changed? The normal force. Am I convincing you yet, Kiowa? I'm not done. Can we increase the normal force? Sure. Example 4. Because there's an external force also pushing down. What's the normal force here? Well, you know what? Let's do a free body diagram. What are the forces acting on this mass? Get the obvious one. Is there anything else in the downwards direction? I'm going to put that just off to the side like that because I don't want the arrows to overlap. Is this object sinking into the ground like quicksand? Say no. Is this object flying into the air like Superman? Say no. So that means my upwards force and my downwards force have to cancel out. In other words, the normal force is going to be mg plus 15. The normal force is going to be mg plus 15. And I figured that out. I actually used Newton's first law. I said, if it's not accelerating, it's not sinking into the ground like quicksand, not flying into the like Superman, short version, if it's not accelerating, forces must be balanced. Everything down has to equal everything up. Did they give me the mass? Yeah? Oh, so it's going to be 5 times 9.8, not negative in this unit, Josh. We decided for the purposes of this equation to let negative be positive. It was easier just to let down be positive, plus 15. So we're never going to put a negative 9.8 in this unit. We're just going to put the 9.8 in. We'll take care of the direction ahead of time with our winner minus loser. 5 times 9.8 is 49 plus 15, 50, 6. Is the answer 64? Yeah, I can do math in my head. Hey, given the net force on each object, fill in any missing forces, and then circle yes or no if the object is accelerating. You know what? Let's do that last part first. Yes or no, is the object accelerating? The object is accelerating if the net force is not what? 0. In other words, that's not accelerating. That has to be, that has to be, that has to be, because I glanced at F net for each of them and it wasn't 0. Wasn't 0. All right. Let's fill in missing stuff. If my net force is 0, how big must A be? 50 newtons. It's got to cancel out the other one. How big must B be? So a net force of 0 doesn't mean there's no force. Is that, Kiowa, can you see now? Is that big enough? I think it was too small before. Okay. Doesn't mean there's no force. It just means everything cancels out. If the net force is 900 newtons up, how big must C be? Got to be 1100 newtons. Right? If the net force is 60 newtons to the left, how big must D be? $20? How big must E be? It's got to be. And this is where we're now saying, oh, that would be, if this was an object on a floor, that would be gravity down. There's your normal force up, and that's why it's neither sinking into the floor like quicksand or flying into the air like Superman. Because if they weren't even, it would have to be. That's Newton's first. 30 newtons to the right. How big is G? Even though you don't know what F and H are, how are they related to each other? They have to be the same. They could each be 819 newtons. That would still give you a net force of 0. Yeah, they end up canceling each other out. So I could say, and force F equals force H. Or if you wanted to put a vector component in there, you could say negative force F equals H if we wanted to include some kind of a direction. But all I know, same magnitude. Same magnitude. Let's keep going. Air resistance. Air resistance is the force of air molecules bumping into an object that's moving through the air. The force of air resistance always has a direction opposite to the way you're moving. I'm assuming all of you at least once have stuck your hand out of the window of a speeding car, and you've done the whole turn your hand sideways and kind of flown it through the air, and you've noticed that as the area gets bigger, the cross-sectional area gets bigger, air resistance gets bigger. If you tilt it like that, air resistance gets smaller, and you probably noticed if you go faster, air resistance gets bigger. If you go slower, air resistance gets smaller. Air resistance, very difficult force to analyze properly. We can only do some very basics with it. Example 4 says, draw a force diagram for each of the following. By a force diagram, what I really mean here, Amelia, free body diagram. Probably. I retyped this on the weekend and I forgot to change the numbers. Sorry. That's next year. What we're talking about here is a ball being thrown, and what I really mean a ball being thrown is, look up, look up, look up, this right here. That part. B is right after it leaves my hand. C is when it's on its way down. Okay? So let's do a ball being thrown. What are the forces acting on it? Let's represent the ball with the dot. What are the forces acting on that ball? Get the obvious one. What else? Well, look at my, look. If I do this, what direction is the ball accelerating? So there must be a bigger force than gravity up. I'll exaggerate it. I tend to exaggerate just to make sure I don't accidentally forget who the winner is. What force is that? You know what? I agree. I'm even going to call that the applied force. My hand. You could, if you really wanted to, you might even almost want to call it like a normal force because it sort of is a surface. Whatever. Sure. That's why it has to accelerate up, because there's an unbalanced force up. Okay, I let the ball go. It's in the air. It's moving upwards. What are the forces acting on it? Get the obvious one. What else? It says include air resistance, so I'm going to tell you there is air resistance. If the ball is going upwards, what direction is air resistance? I'll do it right beside it because I don't like doing overlapping arrows. That's confusing. Which way is this ball accelerating? Which way must this ball be accelerating? Up? There's not a single force pointing up in the diagram. Which way must this ball be accelerating? It has to be accelerating down. It can't be accelerating up. It can be traveling up. Its velocity could be, I don't care about that. I'm telling you it's accelerating downwards. Since it's traveling up, what we would say it's slowing down. I'm telling you it's accelerating downwards. What about on the way down? What are the forces acting on it? Get the obvious one. By the way, this is going to be a free body diagram, and get the obvious one is going to be the equivalent of the T-table from the last unit. This is going to be your, hey, I can write something down, Alex, I feel better. Okay? What else? Air resistance, always in the opposite direction of motion. If it's falling, if its velocity is downwards, what direction is air resistance now? Up. would be getting slowed down a little bit. Now, a ball is pretty aerodynamic. If you replace a ball with a parachute, oh, hey, now air resistance, because you got a bigger cross-sectional area, now air resistance makes a difference. In example 5, how can the ball be rising if all the forces in 4b, in example 4b, how can the ball be rising if all the forces acting on it are downwards? Are all the forces acting on it downwards? Yeah. But when you throw a ball and it leaves your hand, is it traveling upwards? Yeah. Why? This is key. What does all caps mean on the internet? Velocity and acceleration don't have to be in the same direction. Okay, I'll tone it down, but they don't. Eventually, they'll end up in the same direction. Eventually, I'm telling you, the ball's going to come to a stop and start coming back down. Doesn't have to be the beginning. That's something that's tough for people to work their brain around as well. I see a lot of people, they say, oh, if the ball is going upward, there must be a force upwards. No, no, no. If the ball in example 4c is speeding up, write a net force equation. If it's speeding up, which force is winning? Look at your picture. If it's speeding up, which force is winning? Spence, you're right. Which force is losing? 4c. It's this picture right here. It's this picture right here. Is air in the same direction as... Now, if I wrote this equation, it would be gravity plus air resistance, because they're both winners. Here, gravity minus air resistance. Gravity's the winner, and I'm letting down be positive because it makes the math much nicer. It would be nearly done. And then I have a video of me jumping out of an airplane. Some of you have seen it before. Have I mentioned lately I jumped out of an airplane? Because, anyways. 90-kilogram parachutist free falls for a time and opens a parachute. Check. The parachutist slows down. You know what? I'm going to underline the word slows down. I think that's going to be important. At a rate of 1.5 meters per second squared. A says, compare the forces that act on the system. That's physics speak for draw a free body diagram. So I'm going to do A over here. What are the forces acting on this parachutist? Get the obvious one. Spartan, a bit of a pattern, a bit of a trend, a bit of an approach. Yes? What direction is this person traveling? Down. Are they speeding up or slowing down? So what direction are they accelerating? They're traveling down, but if they're slowing down, what direction must they be accelerating? Up. So what direction must the bigger force be? See how we put that together? That's Newton's first. That's the usefulness of Newton's first law. I know there's a force bigger that way. What force is that? Well, since we're talking about a parachute based on our last couple of examples, I think I'm going to call it F air. That's fair? Very nice. I've never done that joke. I am adding that to my repertoire for the rest of my teaching career. Thank you. You've given me a lame joke that is so bad that I can use it. That's fair. Okay, thank you. I've never noticed that before. Honestly, I'm amazed that I didn't, because that is so bad. That is my style of humor. Thank you. Write a net force equation. B. Who's winning? Who's losing? So it's going to be winner minus loser equals MA. There's my equation. I just did B. What does C want me to find? How would I get the air resistance by itself in that equation? Plus the mg. There. if you try and do all this in your head without a free body diagram, it's going to be a nightmare. You're going to get stuff wrong. But I'm telling you, the 1 second it takes to do a free body diagram, this may be the single best tool I give you in Physics 12 for forces. It's going to be... Double check, did they give me the mass? Yeah? Did they give me the acceleration? Did they give me the mass again? Yeah. G, 9.8, not negative. I took care of that, how I wrote this. Oh, it's plug and chug now. 90 times 1.5 plus 90. Hey, can I do that in my head? It's going to be 10.8. It's going to be 11.3. It's going to be 90 times 11.3. 90 times 11 is going to be 909. I'm close. I should be able to do this in my head. Oh, I don't even want to hit equals. I want to, forget it. 1017, yeesh. Oh, to 3 sig figs, it'll be 1020, right? Now, right around now, someone usually said, hey, Duick, this is garbage. Why? Well, if he's accelerating upwards, he'd never come down. This is why air resistance is so difficult. As soon as he slows down, what happens to the force of air resistance? Gets bigger, smaller, or stays the same? Gets smaller. And when this gets smaller, this eventually is going to reach 0, and now you're going to be at equilibrium. Okay? So you're not. We could walk around with it. Yes? It's why you hit terminal velocity. In fact, I think I have it in my notes a bit later. So a good preview of coming attractions. Oh yeah, there you go. It says, the force of air resistance is actually not a constant value. It gets larger as speed increases. A falling object will eventually reach the point where the force, I keep forgetting to fix that, the force of air resistance equals the weight, mg. And we call this steady speed terminal velocity. Looking at the parachutist mentioned above, what would be the force of air resistance be once terminal velocity was reached? Well, once you reach terminal velocity, you're not accelerating, right? So look at this equation. If A is 0, what does air resistance end up equaling? mg. Because m times 0, if A is 0, just leaves you with the mg dropping down. Parachutist jumps out of an airplane and free falls. They reach a terminal speed and they maintain that speed for a while. They then open their parachute. They quickly reach a different terminal speed and descend to the ground. Sketch, can you cross out the word velocity? We're going to do a speed versus time graph. The reason is, technically velocity, everything would be negative, and I don't want my graph to be below the x-axis. I'm just going to graph how fast you're traveling, speed. So, okay. And really what I mean here is vertical speed. So I jumped out of an airplane. I've mentioned that I jumped out of an airplane. When I was in the airplane, before I jumped, what was my vertical speed? Meant to be really obvious. 0. So here's me in the airplane for however long. Geronimo! I jump. What happens to my speed? Straight line or curve? Well, the speed equation doesn't have squareds in it. It's VF equals VI plus AT, so I think it's linear. Wait a minute. I got to take that back. Because now we're including air resistance. As I fall faster, what happens to air resistance? So you know what would happen? It's okay. I'm not testing you on this. I do this on purpose. It's worth making a mistake to correct it, to see. I think what would actually happen is I start out falling fast, but I gradually stop accelerating, and right here is terminal velocity. And I continue free falling. I pull the chute, now what? New terminal velocity. Now, my time scale is going to be garbage because when I jumped out of an airplane, I mentioned that I jumped out of an airplane. When I jumped out of an airplane, free fall was only about 25 seconds, and then the parachute drifting was about 5 minutes. But I don't want my graph to go all the way off the page and over there, so this scale here should be way longer. Can we just imagine that because I can't fit it on one page? Then I get to the ground. What's my final speed once I get to the ground? There. The ground applies the force to bring me to a stop. Looks kind of like the side of a VW, little Beetle. My scale might be wrong. I think the shape is right. Okay. It says, explain for each section of the graph in a few words what's happening. I think we just did orally, so I'm not going to write it up. Homework, and then I'll show you a little video. 1 is good. 2 is good. 3 is good. 1, 2, 3 so far. 4 is good.
5.
Yep. And 6.
We should just skip like 7, 8.
No, I'm going to go 7, but I'll pass on 8. 9 is parachuting. I love skydiving. 10 is tricky unless you set it up right. So if you want to, you can put a little star next to 10 and say, this is an example of a multi-step Physics 12 B plus, A minus level question. And I am going to see if you can handle those. 11, 12, 13, skip 14.